Okay. Okay, let's discuss today about the structural elucidation of sucrose. Today we have a sophisticated instruments. Using the instrument, we can find out the molecular weight. We can find out the amount of carbon is present, amount of hydrogen is present, how much oxygen, how much hydrogen, how much carbon is present in a unknown compound. Unknown, how the unknown compound will get? Suppose if we are synthesizing a unknown compound whose structure is not aware, then one should go for a analysis. By doing analysis, one can conclude the structure of a unknown compound. So, but today we have a sophisticated instruments. Using that, we can find out the structure within a 1 hour or 30 minutes or something like that. But in olden days, it was not like today's technology. In olden days, scientists used to do several reactions, and they took several years to conclude the structure of a unknown compounds. So in that context, we are discussing the structural elucidation of sucrose. So when sucrose is isolated from the natural source, it is found that it is a solid. Then that solid, when it is subjected to CHN analysis, it will give you the empirical formula. So later on, the empirical formula is converted into a molecular formula. And the structure, the molecular formula of the sucrose, it is found that it is having a suitable H22O11. And after knowing the molecular formula of the sucrose, and sucrose was taken and it is subjected to hydrolysis in presence of acid. So you know that sucrose is a on hydrolysis. Sucrose on hydrolysis, it gives equimolar mixture. So equimolar means same concentrated products. So what are the products? One is D-glucose, another one is D-fructose. This shows that sucrose consists of glucose and fructose unit. How the scientist will come to know that this compound is glucose, this compound is fructose? Again, by doing analysis. So you know that glucose contains CHO. And again, glucose subjected to CH analysis, and after by calculation, with the data of CH analysis, we can conclude that empirical formula and molecular formula. Similarly for the fructose. And you know that the difference between the glucose and fructose. So glucose contains an aldehyde group, whereas the fructose contains a ketonic group in open side structure. So in ring structure, glucose does not contain aldehyde group. In ring structure, fructose does not contain a ketone group. So here what we need to take, sucrose on hydrolysis in presence of H plus, it gives two units called D-glucose and D-fructose. What it indicates? It indicates that sucrose is formed by the combination of D-glucose and D-fructose. Otherwise, sucrose contains two units called D-glucose and D-fructose. And one more thing, since sucrose on hydrolysis gives two carbohydrate monosaccharides, that means sucrose should be the disaccharide one. Then sucrose, that means I'm talking about the sucrose, I'm not talking about the glucose or fructose. Sucrose is a disaccharide and it does not reduce Tollens reagent or filling solution. What is Tollens reagent? Ammoniacal silver nitrate is the Tollens solution. What is filling solution? Filling A, filling B. Filling A copper sulfate, filling B is sodium potassium tartrate. Okay, then what happens when sucrose is added to toluene. Toluene does not reduce that means there is no silver mirror formation. So if there is no silver mirror means uh, sucrose does not contain free aldehyde group, and at the same time sucrose does not contain free ketone group. Similarly, sucrose, when it is treated with Fehling solution means Fehling solution is nothing but a Fehling A, Fehling B. Fehling A is copper sulfate, Fehling B is sodium potassium carbonate. So what will happen? Fehling's also does not react with the sucrose. What it means? It does not form posazole. And that means when you are treating with usually aldehyde or keto can undergo osazole formation when it is treated with phenylhydrazine. So that means what it indicates? It indicates that sucrose does not contain aldehyde and keto in its structure. It does not undergo mutarotation. I think you know that what is mutarotation. So you know that structure of glucose. So glucose in solid form, it can be available in the form of alpha D glucose as well as beta D glucose. Alpha D glucose will have a optical rotation of 118 degree, and what you call beta D glucopyranose optical rotation is 18 degrees centigrade. So when these two are dissolved in water, so what will happen? Slowly, alpha D glucopyranose is converted into it is in equilibrium with the open chain structure. Beta D glucopyranose also converted into a open chain structure in solution in water. So what it indicates, if you are recording the optical rotation, it shows that 1118 optical degree is slowly changes to 52.6. Similarly, 18 optical rotation of beta D glucopyranose slowly converted into 52.6 optical rotation. 52.6 is the optical rotation of what is called as open chain structure of glucose. This changes from alpha D glucopyranose to open chain structure of glucose and beta D glucopyranose to open chain structure of glucose. This change in rotation is called mutarotation. What it means? So it means that sucrose does not undergo mutarotation. So suppose sucrose does not undergo mutarotation means what it means? It means that there is no free anomeric carbon atom in glucose as well as fructose. All these facts indicates that sucrose does not contain free aldehyde or ketonic group. Thus, the two exoses. Exoses means glucose is one exose, fructose is also an exose. Must contain glycosidic linkage. So, glycosidic linkage means the oxygen. Oxygen is bonded to glucose as well as fructose. So that is called glycosidic linkage. Glycosidic linkage between C1 of the glucose and C2 of the fructose. C1 of the glucose. That means the what it means? It means that in sucrose, D-glucose and fructose are joined through glycosidic linkage. Okay. And more particularly, C1 of the D-glucose is involved in a glycosidic linkage and C2 of the fructose is involved in a glycosidic linkage. That is the reason there is no free ketone in fructose. There is no free aldehyde group in glucose. So because only in this way, the single between the two units effectively block both the carbonyl group. Here, carbonyl group means aldehyde group present in glucose and CO group present in fructose. So up to this, what we learned? We learned that the molecular formula of sucrose is C12H22O11. So sucrose on hydrolysis gives two products called D-glucose and D-fructose. It indicates that sucrose is formed by the combination of D-glucose and D-fructose. So when sucrose is treated with tolerance reagent, it does not give you silver mirror. When sucrose is treated with filling solution, it does not reduces the aldehyde or ketone present in the sucrose. So, and sucrose also resists the formation of oxazone when it is treated with vinyl hydrogen, and it does not undergo methylation. Okay, all these experiment shows that the sucrose does not contain free aldehyde group as well as the free ketone group. So that means there is no free aldehyde, there is no free ketone. It indicates that there is a linkage between the C1 of the glucose and the C2 of the fructose in the form of glycosidic linkage. So with this, I will go to the next slide. So here I'm taking the stereochemistry of the stereochemistry of the glycosidic linkage experiment done. Sucrose is hydrolyzed by alpha D glucose. So this is alpha glucosidase is an enzyme. Okay, what it will do? It will hydrolyze the sucrose into a alpha glucoside pyranose, and so alpha configuration of the glucoside pyranose. Similarly, sucrose is hydrolyzed by sucrase. This is an enzyme. This indicates that beta configuration at the fructose side of the position. So here, so I think you are aware about the stereochemistry. Stereochemistry means retention of configuration. So for that retention of configuration, two enzymes are used. One is alpha glucosidase. This is an enzyme. So when sucrose is hydrolyzed by using an enzyme called alpha glucosidase, so this indicates that alpha configuration of the glucose side. So that means you know that sucrose contains two units. One is glucose, another one is fructose. So glucose unit is alpha configuration. How this is concluded? By treating a sucrose with alpha glucosidase enzyme. So this indicates that alpha configuration is present at the glucose side. Similarly, when sucrose is hydrolyzed with sucrase enzyme, so this indicates that beta configuration at the fructose side. Okay, so again I will explain this particular one. So that means sucrose is joined by the combination of glucose and fructose. So more particularly, alpha D glucopyranose is joined with the beta D fructopyranose. Okay, so then only alpha 1,2 linkage. Right. The size of glucose and fructose units have been determined as follows. How do you find the size of glucose and fructose present in a sucrose? So then you have to answer this particular one. So sucrose is taken and it is subjected to methylation. What is methylation? O methylation, C methylation, S methylation. Sulfur means alkylation. So dimethyl sulfate is an alkylating agent. So what it will do? It will convert a hydroxy group into alkoxy. So a sucrose, when it is treated with the dimethyl sulfate in presence of sodium hydroxide, so it gives octa-O-methyl sucrose. Octa-O-methyl sucrose. That means here one methyl, this is 1, 2, 3, 4, 5, 6, 7, 8. There are 6 methyl groups. The name of this compound is called octa-O-methyl sucrose. What it indicates? It indicates that sucrose consumes 2 mole of dimethyl sulfate and converted into octa-O-methyl sucrose. What it indicates? It indicates that sucrose contains 8 hydroxy group. Those 8 hydroxy is converted into alkoxy. So that's what we can conclude in this slide. So with this, we'll go to the next slide. So the obtained octa-O-methyl sucrose subjected to hydrolysis. So hydrolysis means treating with an acid. So what will happen? So there will be a linkage, glycosidic linkage cleaved. So once the glycosidic linkage is cleaved by the hydrolysis, what you will get? A aldehyde to the glucose unit and ketone to the fructose unit. So then what are the products obtained? Second position, methyl group, O-methyl. We are talking about the methyl, O-methyl. Second position, methyl group. Third position, methyl group. Fourth position, methyl group. Sixth position, methyl group. So totally 4 methyl groups. That is the reason tetra-O-methyl D-glucose. Why it is D? Because here the OH is at the right hand side. So that is the reason it is D. So name of this compound is called 2, 3, 4, 6 tetra-O-methyl D-glucose. Similarly, what is the name of this compound? This is 1, this is 2, this is 3. That means 3 position O-methyl is there, 4th position O-methyl is there, 6th position O-methyl is there. So 1, 3, 4, 6 tetra-O-methyl D-fructose. Why it is D? Because hydroxy group. This hydroxy group is on the right hand side. So these two are the products obtained. When these two are the products is obtained, sucrose undergoes methylation followed by hydrolysis gives 2 products. What are these 2 products? This you can term it as a 1. This you can name it as a 2 in a Roman letter. The identity of the products, this is 1 and 2, show that glucose position is a pyranoside. So what if this is a 6-membered ring and aldehyde is present at the first carbon atom and it is in a ring formation, means in the previously it was in ring formation and it is pyranoside. And you know that this is a fructose, and definitely fructose means it's a furanose 5-membered ring. There will be interaction between this hydroxy and this carbon. How many carbon atoms? 1, 2, 3, 4 carbon atom and 1 oxygen, 5-membered ring, and it is called furanoside. So just by looking these 2 products, we can conclude that the linkage present in glucose unit is 1,5. The linkage present in fructose is 2,5. That's what we can conclude with this structure. So with this, I will go to the next slide. So in the next slide, in order to explain about the above facts, glucose, it is in the form of alpha-D-glucopyranose, and fructose, it is in the form of beta-D-fructofuranose. And so in order to explain the above facts, what we can do, we need to couple the alpha-D-glucopyranose is taken and the beta-D-fructopiranose is taken, and it was a glycosidic linkage is made. Okay, so what I'm making here, 1 minute. So I have to add. Okay, here there is a glycosidic linkage. So here a glycosidic linkage is there. Okay, let's take a pointer. Okay, so this is a glycosidic linkage is there. Okay, oxygen is there. So that means that this is a glucopyranose, and this is the fructofuranose. These two are joined, forms a disaccharide, and the name of this disaccharide is alpha D glucopyranosyl. That means this one, alpha D glucopyranosyl. And this one beta. Why it is beta? Because the hydroxy in beta is on the left hand side. Beta D fructopyranose. Pyranose means 5-membered ring. 1, 2, 3, 4, 5. 5-membered ring. That is the reason pyranose. This is the structure. How this structure is obtained? By the combination of. Why we need to combine alpha D glucopyranose and beta D glucopyranose? To compare these product with the result obtained, the previously obtained compound. What is the previously obtained compound? The structure during the structural elucidation, the obtained one, and this one is comparison. So with this, I will go to the next slide. So by doing all this experimental data, we can conclude that the structure, sucrose structure is given, and in this sucrose structure, this one is called as a alpha D glucopyranose, and this one is called beta D fructopyranose. And here the linkage between the two glucose units is alpha 1,2 glycosidic linkage. And these two are the Haber structure, and these two are the conformations of glucose. This is the conformation of glucose, and this is the Haber structure of glucose, or not the glucose, sucrose. So sometimes they will ask you directly write the Haber structure of sucrose. So then you have to write this. Sometimes they will ask you write the conformation, more stable conformation of sucrose. Then you have to write this one. So this was the structure proposed for the structure of sucrose. And there are some chemical evidence for this structural elucidation. So let's look into what are the chemical evidence for the structural elucidation of sucrose. Let's go to the next slide. So this is the one chemical evidence for the structure. So what is the name of this compound? Name of this compound is called alpha D glucopyranosyl. This is the one. Alpha D glucopyranosyl, beta D glucofructose. This is a prepared one. How this is prepared? By the combination of alpha D glucopyranose and beta D glucopyranose subjected to dehydration, giving rise to glycosidic bond formation. Then the obtained alpha D glucopyranosyl, beta D glucopyranoside subjected to periodic oxidation. So periodic oxidation is a oxidizing agent. So what it will do? It will sleeve the what is called as glycosidic linkage. Okay. More particularly in this unit, this particular center CHOH is converted into carboxylic acid. This carbon is going out as a carboxylic acid, and this carbon, you know that alcohol is there. Alcohol is converted into aldehyde. This carbon, alcohol is there, is converted into aldehyde. I will repeat again. In this alpha D glucopyranosyl moiety, when a periodic acid is treated, the center carbon is converted into carboxylic acid. This carbon is converted into aldehyde. This carbon is converted into aldehyde. Similarly, in this one, so there will be a breakage here. So the glycosidic bond breakage, it is possible with the peroxide. So what will happen? This alcohol is converted into CHO. This alcohol is converted into CHO. So alpha D glucopyranosyl, beta D fructopyranoside, when it is treated peroxide, so it will give you the tetraaldehyde. Okay, tetraaldehyde intermediate with the liberation of carboxylic acid. So this carboxylic acid is released from the glucose side moiety, and the obtained aldehyde subjected to oxidation, using the mild oxidizing agent. That means this CHO, this CHO, this CHO, this CHO is converted into carboxylic acid. It's a mild oxidizing agent. Addition of oxygen, CHO is converted into COOH, CHO is converted into COOH, CHO is converted into COOH, CHO is converted into COOH. The obtained compound is subjected to hydrolysis. Hydrolysis means glycosidic hydrolysis as well as furanose furanose hydrolysis, fructanose, this is also hydrolysis. So this moiety is subjected to hydrolysis that I am explaining in the next slide. I will go to the next slide. So on hydrolysis, this part is coming. This is one fragment. This is another. 4 fragments are coming. Okay, I will go back to the previous one. So this part, okay, that means here CHO, CHOH, COOH, and here COOH, CHOH, CH2OH, and then here OH, breakage here OH is coming. That's what I am written here. So that means this is a glycerol. Of course, this is also a glycerol. Of course, this is also a glycerol. Of course, this is also a glycerol. So what will happen? You can observe that 2 hydroxy groups are there. This is the glycerol. This is also a glycerol. But here 2 hydroxy group. And here also 2 hydroxy group. So you know that if the 2 hydroxy group is attached to the same carbon, such diols are unstable. What they will do? They undergo dehydration. How the dehydration? H and OH is going out. This bond pair is coming over. That means a ketone is formed. This one. So glyoxaldehyde. Name of this compound is called glyoxaldehyde. After removal of water of this moiety gives glyoxaldehyde. Then removal of water from this moiety also. OH minus will go out as a water molecule and converted into hydroxypyruvate. This one. So this is called hydroxy. Okay. If in place of OH, if there is a H, is called pyruvate. Since it contains hydroxy, we will call this as a hydroxypyruvate. And these 2 units are the glycerol moiety. So this is about the previous slide as well as this slide is nothing but a chemical evidence for the structural elucidation of the sucrose. So particularly sometimes they will ask you 4 marks or 5 marks questions. They will ask you to write what are the chemical evidence for the structural elucidation of sucrose. So in this carbohydrate, you have 2 disaccharides structural elucidation. One structural elucidation is sucrose, another structural elucidation is maltose. So between these 2, one you will get in your main examination. So this is about what is called as structural elucidation of and their chemical evidence for the sucrose structure determination. Okay, that's all about today's class.